you hear me? Can you see my screen?
Good day.
Good day, yes.
Okay, fine. So, before to start, I would like to say that unfortunately on Monday I have a very important meeting. So exactly in this time, and I can't skip it. So can we discuss and to choose some other day where I can give this lecture? Are you here?
Yeah, we can.
Or maybe you can discuss it later, and we
Yeah.
can okay. So as I understand, you would like you prefer to discuss it in advance before. I mean, with you, and after this to write me when it is possible to meet with you to give this lecture.
Yeah.
Okay. Okay. So I will wait your suggestion in Telegram channel. Thank you very much, but it's really I already miss a lot of things where I need to be present, and I would like to be present due to the lectures. So, but this time I really it's important. So okay, let's continue. And we in the previous lecture we succeeded. We found Einstein equation for gravitational field. And yes, the second question that I discovered that we will have the additional lecture, which will be on Saturday, starting from I don't remember this week or next week. So it means that we will have 3 lectures during a week. This is not my invention. This was made by university because they decided to finalize educational process early in the beginning of the December, and as usual, they decided to do much more lectures during week now, and after this we will finalize everything early. So I hope that you have this information when we will have additional lecture. Do you have this information?
Yeah, we hear.
Okay, so in any case, I will remind you in Telegram channel when we will have lecture Saturday. So now we will continue, and yeah, we stopped on this point. So we found, we obtained Einstein equation, and we also discussed that even if we don't have any distribution of matter, so it means that the right part of this equation equals 0. We wrote it like this. So it means that 10 to the reach equals 0. This is Einstein. Can write Einstein equation for empty space. Empty space. And as I said to you, this is equation where black holes was born in sense that so, and we will speak a little bit about this later. And now I want to come back. I want to come back to this point. I want to come back to this part where we found the expression for metric tensor. For the case of the weak field. And as you remember, we tried to generalize the equation for gravitational field for classical mechanics to generalize it for the relativistic case, which we finally succeed using this idea which we had. Again, I would like to say that, of course, we can obtain Einstein equation writing the action of gravitational field and action of the matter, and after this to consider the variation of this action, and due to the rules that the variation of the action equals 0, we also can obtain Einstein equation. I will not do it, so if principle, I can give you some formulas, but and you can look at this exactly in Landau-Lifshitz book, the theory of field. You can find exactly this proving, but it's really much more complicated and long. So we don't have, unfortunately, a lot of time, and this proof is also okay. Now I want to discuss some peculiarity which appeared in such a kind of field using this expression for metric tensor which we obtain. So we can write the title. Just a second, we need to answer. Okay, so proper. Oh, I'm not sure that I write in English. Right, I just. Yeah, right. Yes, proper time. Proper, and in principle, can call also, and coordinate time. So this is exactly the point, and we already could meet with such a kind of things in special relativity, but in this case we, for example, will see some properties of the strong gravitational field which now try to be discovered, also they discovered due to observational data in astrophysics. So what it means? We can consider, for example, when we speak about interval, about events in general relativity. So it means that each event we can recognize and to clarify if we know the corresponding coordinates and time and moment of time of this event. So it's understandable because when you, for example, make some meeting, you need to say the time and coordinates. In general and special relativity, starting from the special relativity, we exactly using the event interval ds. As you remember, we used it already. So, and starting from special relativity, the time and space are connected in one metric. So, and due to this fact, also we meet some differences between two kinds of the time. For example, so we can put the definition. When we use the coordinate in our metric, And here we use I from 0 to 3. And 0 corresponds to the time coordinate. So it means that x 0, 0, we can call this x0 as a, if it will not take into account the speed of light for now, for example, we can call x0 as a coordinate time. So because it's included in as a coordinate in interval between two events. From another side, the same interval delta, let's consider as delta x0, in different points of the space corresponds a different interval of such a kind of proper time. So in proper time, usually we use the letter tau. Proper time, what it means and how we can find the connection between coordinate time and proper time. For example, let's consider the situation when we have two events, 1 and 2, they're next to each other in the space. Doesn't matter. We can even now we will clarify what we consider the two events, and these two events. Let's consider these two events are located in one point of space, the same point of space. It means that dl square equals 0. So since we consider the s square as a t square dt square, no, it's not a good to write because I wanted to write the Minkowski space, but it's not. So we can, in this case, since we erase the part which is related with the space part of the metric, so we will have in this case that ds square equal c square d tau square. So this is, we understand even, in principle, understand it from special relativity. So in special relativity, like if it could be not in the same space, you could write this minus dl square, but so the same space, the same point in space between two events, 1 and 2, and this dl which equal 0. So this is from one side. From another side, if we will consider the more general case, so general relativity, we can write it in general case, the metric ds square equal, okay, wrote above, like I repeated here, xi takes k. So, but since again we decided that these two events were in the same point of space, it means that this part of the space will disappear, and we will have only J00 dx0 square. So this is equal this square due to the fact that the L equals 0. So in this case, if we will compare this one and this one, so it should be the same. So the interval should be the same in any reference system. This is scalar. We can write, we obtain exactly this correspondence between coordinate and proper time, which will be this one. Okay, or we can write that the proper time equal 1 divided on c square root gen 0, 0 dx 0. So we can put it in some frame. And if we will consider, for example, the case of the weak field, so for the weak field, we found this J0, 0, which is 1 plus 2 phi divided on c square. So we obtain that proper time equal minus divided on c square root 1 plus 2 phi divided on c square x 0. In principle, we can even to remind that x 0 equal c multiplied on t, and if again we can consider the t as a coordinate time, so it's different. So in principle we can rewrite this like this: d tau square root 1 plus 2 phi divided on c square multiply on t. So this is also don't keep the speed of light. Again, I would like to remind that phi this is dt. Sorry, this is of course it's not correct because it should be d and dt. Okay. So where phi, this is gravitational potential. Phi is a gravitational potential, Newtonian gravitational potential in this case. So this is a, as we say, post-Newtonian terms of general relativity consideration. So this is weak field, but in any case, we keep this memory that we are considered general relativity theory. So, and writing this through the classical gravitational potential. It's understandable that, for example, this summand is dimensionless. So, because as we remember, phi, this is gm divided on r square, and which correspond to potential energy, counting the sign. And if you remind the conservation law, v square equals gm divided on r. So we understand that if you divide on the dimension of the speed of light, the potential, this is exactly dimensionless value. Okay. What it means? Also, we can, since we consider post-Newtonian, as we say, consideration, so this is a non-relativistic case, but we keep c square. We can we understand that this value is small, and we can consider this square root as a series, and we can write that the tau equal approximately. Okay, and so we kill a square root, but we remember that when we consider series of square root function, square root from function, we need to put this is 1 plus 1 divided on 2 on function. So we need to write 1 plus, and we will have phi divided on c squared dt. So if we again will take into account that the potential, like we decided potential, is a negative value minus gm divided on r for the point mass. In this case, we can write the tau 1 minus, and here we will put model c squared dt. What about this expression tell us? Look, when we say about proper time, it means that this proper time is related with a clock, which are, I might say, in the hand in a moving reference system. So if we will consider some person who, for example, would like to understand what is the proper time, this is exactly time which will be shown by his clock. If this person observer move in some gravitational field. So, but what we can see is that if by absolute value the gravitational potential is higher, then proper time will go with more slowly, because you can see that. So if model phi more than like this, right? Okay. So in this case, d tau will be less than dt. And the conclusion which we can do in this case, it means that, and you can write that proper time is going more slowly in gravitational field with higher by absolute value, with a higher potential by absolute value. So again, I will repeat that proper time are going slowly, more slowly in the field with higher value of potential by absolute value. So it means that if we will consider these 2 points, ground, planet. So here and here, here it will be phi1, phi2. So in this case, phi1 more than phi2, so gravitational field by absolute value. Okay, put absolute value. So the time here, the tau will be, the tau 1 will be less than the tau 2. So this is a consequence of general relativity. In principle, it means that if you are on the surface of the planet Earth, so, and if you compare and you have your clock and you have your friend who are in some altitude on some 100 kilometers, like astronaut. So, and if you will compare your clock your clock will go more slowly than the clock of the astronaut which are on the orbit. In principle, it's not so surprised because when we spoke about special relativity, we had such a kind of things because also when you have a clock, the observer with the clock which are moving with a relativistic case. In this case, as you remember, you also have a Lorentz cutting of the time. So, and in general relativity, I think it's not right, maybe word. In this case, we also have such things. And this point really was even to check experimentally. So, for example, one of the experiments which was done, this is using flight with the atomic clock. And it was really proved that this consequence of general relativity is right, because really it was discovered that clocks on different altitude are going with a different, like say, with a different speed, like this. So this is one of the points. The second one, are you here?
Yeah, we can.
Good. This point very important for astrophysics, not only in principle. We can immediately to understand that this property bring us to some interesting conclusion which are related with changing of the frequency of the emission. So, and I would like to tell a few words about redshift. Redshift. In this case, I even would like to say this. Gravitational. Redshift. Redshift, we already met this words redshift. And you exactly in this point, and it will be some question on exam and principle, you need to understand that it can be 3 possibilities to have redshift. Redshift, it means that this the emission, Mama mia, what's happened? Somebody, just a second, let me check. So redshift, it means that we have some line in spectrum, and this line, which, for example, correspond to the green part of the spectrum, due to some processes, physical processes, shift in red side. In red, it means in the side with a larger wavelength. So, and as we know, it can be, we already know that the reason why it can be happened, we already know that the first, this is Doppler effect. This is remind. The first, this is Doppler effect. So in Doppler effect, we understand the idea of this effect that if you have some, we consider this in the beginning, if we have some source of the electromagnetic wave, so and the source is moving, so it will be the shift of the line on the red side if this motion from us. If to us, it will be blue shift. This is the first. The second one, no, correct, redshift. Left and red, and in principle can be blue shift as well. So, and we even discussed that this problem that we, from observation, we can see that galaxy, almost all galaxies have a redshift in their spectrum. But we discovered, we discussed it, that we can't interpret it as a Doppler effect. So it looks like all galaxies go away from us, but this is not a point to explain cosmological redshift. So cosmological redshift. Cosmological redshift, as we considered in the beginning of our course, and by the way, in the next lecture, we already start to work exactly with the cosmology. We will construct the metric of our world to justify it, why we can describe our universe by this metric, and after this we will see what Einstein equation tell us. But we already discussed that cosmological redshift, this point that galaxy go away from us, looks like go away from us, has a redshift in the spectrum. It's related to the fact that it's related with the stretching of the space. So of our space, and this is different mechanism which creates this redshift for galaxies, for astrophysical objects. For galaxies, I would like to say. So the third one, this is exactly gravitational redshift. So this is different mechanism. Gravitational redshift appear due to the exactly due to the fact that the proper time going slowly, so more slowly than coordinate time, and that the fact that in more strong gravitational field, the proper time will be slowly. So this is exactly the effect of this effect of deceleration of time. Let's see it that it really can bring us to gravitational, to redshift in the spectrum. So how we can see it? Okay. What is the frequency? Frequency, this is, just to remind, this is derivative from of a canal to the time. If we will put coordinate time, we will put here also coordinate time. If we connect this with psi, this is a canal. So this is d tau. Coordinate time, or we can interpret it as a frequency, with the frequency of observer. So in this one is the frequency of emission. So, for example, we can consider the astrophysical situation when we have a black hole or neutron stars, some relativistic object, and we have some electromagnetic wave from the surrounding of this object, this omega emission, and some observer here which receive this emission. Okay, register this emission here. So and we can write what we will see. So in this case, we can write, since we have a relation between d tau, which is in general case, I will write square root g 0, 0 dt. Okay. So I can write that omega tau, which is omega emission. I will put here this, which equal minus dpc by d tau equal minus dpc by dt by d tau. Dt by d tau will be 1 divide square root g 0, 0 omega t. About minus, let's put here model. Because minus we can keep in this 0, 0. So, in principle, it's not important because it doesn't matter. So, because I did stupid things, because this is exactly omega t. Okay, no, now everything is correct. All this is 1 divide 0, 0 omega observation. Okay, so we obtain that omega observation equal minus g 0, 0 omega emission. In principle, this is general formula which we can use for different kind of metric. So, for example, a little bit later, we can use it for example, for black hole. Now I will use post-Newtonian case. So I will, we will remember that due to the fact which we obtained before, observation equal 1. Okay, we look here. Okay. Minus model phi divide c square omega emission. So in principle, we can see that if we have spectrum, okay, let's put here omega. We could put nu. It's the only point to normalize it on the speed of light. So, for example, we have some line which correspond to green. To green part of the spectrum. So in this case, when frequency became higher, it means in this direction. Okay, so it means that we go to the blue side. If the frequency became lower, this is red emission, red shift. And what we can see, so if we will, we have omega observation less than omega emission if model phi, I would like even to write model delta phi, is if we have some value of delta phi. Okay, so if, for example, we go from the place where delta phi, this is what we wrote here, phi 1 mean minus phi 2, phi 1 minus phi 2. More than 0, it means that this is have some value. So stupid to write this. Okay, I will write like this. So phi 1 more than phi 2. So we can see really that when we have or from the if you write for the wavelengths, it means that lambda observation became more than lambda emission. So it means that if we have some relativistic object, this relativistic object doesn't matter. Relativistic object in principle, it can be any object, but the effect much more, of course, much more stronger for the relativistic object, which is a black hole, neutron star, or white dwarf. In this case, so if we have some emission here, to this observer, this emission will come oh, sorry, I wrote otherwise. Okay, so yes, right. Lambda emission more than lambda observation. All right, everything right. So it means that when emission go out from the strong gravitational field, this emission became more red. So this is omega emission, this is omega observation. This fact is taken into account, for example, when we analyze the emission of astrophysical objects. And this is exactly one of the proof of general relativity. Because, and we can see it really, so if you, fixed it and investigated it, for example, if you have an astrophysical object, a relativistic object, and from theory you understand that this emission should correspond to such a kind of the spectrum. For example, you know this line of atoms should correspond to exactly this place in spectrum. But you can see that if this object are related to relativistic object, this line shifts to the right side. So, and it was proved for many objects, including supermassive black hole. When we have a supermassive black hole with accretion disk around, and when we obtain the emission from accretion disk, this emission from accretion disk for the vicinity of black hole, if this is black hole, also show us that there is a shift to right side of the spectrum. So this is one of the tests, I might say, would like to say, of general relativity. And what we can see in observation, which really tell us that this prediction of general relativity is right. So, okay. Do we have some question about this part? No? Okay, in this case, I also would like to tell a little bit, to speak a little bit about black holes. So again, which is really a very interesting point, and because now we are living in the era when we really can investigate such a kind of object, as I already stated before, that when Einstein discovered that it should be some strange solution of his equation, he couldn't at the first believe that it's really right. Why? Because, and how these black holes can appear in general relativity. So we discovered that if we have an empty space, so I can write it black holes. Again, I have a little time to speak about this. You can see only half an hour, so I will try to do it quickly. Black holes. And also it's called Schwarzschild metric. I will time forget how write Schwarzschild because it's a German family, and check now. Black holes. Oh, I write like this. Now we'll see why I decided to, in any case, to check. Metric. So you can see that when we pronunciate it and write in Ukrainian, for example, such as Schwarzschild, it's much more simple than to write it with all letters because it's a German family. So Schwarzschild metric, this is metric for black hole, which not rotate, no, without charge. And this is exact solution of Einstein equation. But by the way, Schwarzschild, it's a German scientist. He found this solution. It's immediately 16, as I remember, 16 years. Yeah. Just check in internet that he found this. He found the exact solution in 1915 and published it in January 1916. I will tell why it's interesting, it's important, because exactly the two papers of Einstein, they appeared in 1915. So immediately Schwarzschild read it. And what is really amazing is that in this case, Schwarzschild was on the war. Here from the Germany side, this is the first the First World War, and he was on the fighting line, and he catch not a cold, he catch some really very strong disease. Due to epidemic, because as we know, during the First World War, much more people died through the diseases which were related with epidemic, not even through the artillery or like this direct fighting. So, and he found his solution in January, it was published, and in February he was died due to this disease. So he was in hospital when he found the solution. And now his name is much more exciting name in science, because when we speak about black holes, we immediately working with Schwarzschild metric. So his son was also a great astronomer. From another side, the same time, from another side was from Russian side was Friedman, Alexander Friedman, who, as we will consider later, obtained the solution of Einstein equation for cosmology. So this is very interesting story. Two persons, great persons, who made a lot of very great things for development of physics. So they were fighting from an opposite side, from German and from Russia Empire this time. Okay, how to find this solution for black hole? So this is if the Schwarzschild considered Einstein equation for the empty space, this one, and he decided to check which, and I said you before that even this equation give us not trivial solution. Which solution will give such a kind of equation? He considered the general metric in the form in spherical coordinates. So it means that let's consider which solution will be for spherically symmetric case. So for spherically symmetric case, if we will, it means that we can keep the last part of the metric. It means that I can write like this. So I don't know what is G00. I don't know what is G11 dr square. I keep it. But the last part I can write freely. It means that it allows us to keep the square of the sphere and the length of the circle. So I write just normally what we know from spherically symmetric part of the metric. Again, where we consider the spherical coordinate system. So it means that this is polar angle, this is zenithal angle. Phi, this is not potential, but okay, I will keep it. And and R. So this is spherical in general case, the representation of this metric, and Schwarzschild looking for this component of the metric which satisfy Einstein equation in empty space. So to prove this, usually we before we had a time we found this solution. Like it's in principle we need to spend one lecture or 1.5. But if you will do all procedure considering this G00, G11 as a sum function, usually it's considered like a function in exponential form, but because it's just convenient, after this is exponent will disappear. So, but it's such a general, I will write like this. Some function phi of time and R, and G11 phi1 F0, okay, F0, F1 of T and R. So, and the problem to find this F0 and F1. Taking into account that finally, in any case, you need everything should justify to the case of classical mechanics. So, if we will do all procedure finally to solve this equation, we will obtain the metric. I will write the final result in this form. C squared dt squared minus d squared 1 minus RG divided on R. And last part, just repeat it. So square theta, delphi square. So this we can put in frame, because this metric has a name. This is exactly Schwarzschild metric. And the object which are describing of this metric, they call Schwarzschild black holes. Why? So this is some strange object, and now you will understand why even Einstein couldn't believe that this solution is mathematically it's right, but from physical point of view that it's really can describe the reality. Because you can see that there is something strange.
I'm so sorry. Can I make some clarification? This gamma capital G, what is it exactly in this expression?
Gamma capital G, where?
For example, d square equal 1 minus gamma capital G divided on R.
This is not gamma, sorry. This is R, G.
Okay.
Which is, yes, it's the right question, because I didn't clarify what is this. This is 2Gm divided on C square. And this is called gravitational radius. Gravitational radius. This is also RG. So gravitational radius. When we say, for example, about, I hope you hear something about black holes. Yes? Are you here? Do you know what is black hole in principle? In some, maybe you saw.
Yeah.
Yeah. So it's a very beautiful point in a fantastic movie. When somebody jump in black hole and something happened on black hole next to some spaceship. So when we say about size of black hole, this is exactly gravitational radius. So, but this is exact solution. M, this is mass. If you say about mass of the object, some mass, okay? C, this is speed of light. G, this is gravitational constant. So what you can, it means that, what tells this metric? This metric tells us which is a gravitational field, how to say it better, which gravitational field can be around concentrated mass, which is we clarified with the letter M. So, this corresponds to spherical symmetric solution, static solution, and also spherical symmetric construction. So now we will see why it's strange. So this is exact solution. If you will put such a kind of metric, it's like, corresponding, for example, the outer potential of the point mass. So if you will put this metric, solid sphere, we obtain this one. But the strange things, this one, because we can see that when r, the distance, r, this is distance from the center of the symmetry. When r equal or tend to gravitational radius, in this case, we have in this summand divide the situation when we have in denominator 0. This is singularity. From the mathematical point, we speak about singularity in solution. Also, we can see that there is also problem in this summand too, because in this case, the part which is related with the time also became 0. So, and this is really strange, and we will see what it means. This singularity, of course, by the way, there are two singularities. This singularity, and singularity when r equal 0. Also have singularity. In principle, when we, for example, speak about classical mechanics, they also sometimes have a singularity. For example, when we consider the gravity of the point mass. So we consider the mass as a point. Since this is zero-dimensional object, we have a singularity in this point. But we don't care about this, because we understand that massive point, this is our invention. It doesn't exist in reality. It's only for us much more simple to consider, instead of solid sphere, to consider the massive point, especially when we're far from this object. But in principle, this is exact solution for the outer potential. In this case, it tells us that such a kind of object should exist. It means that this point tells us that this is like a hole in a space. In principle, this is hole in space and time. Why sometimes it's describing like this. I will try to do it like this. Okay. So, and with the radius, which is equal gravitational radius. So this presentation of black hole. I immediately can tell that really, indeed, on the radius, which is equal gravitational radius, so if such a kind of object exists, for now we can, for example, suggest that it should be really some strange things. For example, again, we now have a general expression for proper time. So we can write the tau equal 0, 0 dt. And for the Schwarzschild metric, we can obtain that the tau equal square root 1 minus rg divided on r dt. Okay, so we can even put it. This is exactly how change the proper time for black hole. So when we speak about a black hole, Schwarzschild black hole, simplest case, we speak about Schwarzschild metric. And what we can see from this, we can see that since gravitational radius divided on r positive value to distance, all time we'll have the situation where the tau less, I even can put here like this dt. We also can see that if we are far from this gravitating object. So we are on the distance which tends to infinity. In this case, the tau tends to dt. So we don't see any differences if we are far from this strong gravitating object. But for example, if and when we speak about proper time, for example, we speak about the clock which are in vicinity of black hole. I will use now the storm of black hole. So, for example, if for us, but dt we can coincide it with observer which is far from black hole. For example, if we have some clock, and this clock is a coordinate time, or we can tell about laboratory time, so far from gravitating object. And t. So, and let's consider that, for example, for our clock, which are far from black hole, we have dt, our clock show 1 hour. Okay, let's suggest that the time which we will consider, so we are on the distance relative to gravitational radius, 0.96. So it means that we are nearby to black hole. Okay, so it's 10 to unity exactly, just to make it much more remarkable, put this number. So it means that 1 divided g divided on r equals 0.04. Okay, if I will put in this formula, I will see that the d tau will be 0.2 dt. So or dt divided on 5. So it means that in 5 times in this case, the proper time will go slowly than coordinate time, the time which are related with observer or far from black hole. So it means that for the observer who are next to black hole, the time will be, the error will be here, move a little bit. So this is such a kind of things which we obtain immediately from this formula. Also, we can see also that if we will consider the observer who are far from black hole, so we can write that in this case dt equal d tau, just to write opposite, square root 1 minus rg divided on r. So, and we can see that this is for observer who are far from black hole. We can see that if r tends to rg, dt tend to infinity if the tau is limited time. What it means? It means that if we have some some body which fallen down in black hole, for the observer who are far from black hole, this body, which next to black holes and fallen down black hole, for him it will look that this body can't reach the horizon. the surface of black hole. So it looks like it's going, but can't reach. But for the body who will go down in black hole, he will cross this special surface of black hole for the limited time. So it looks like this. Why this object is strange? And the second point, why, for example, in the first such kind of object will called as frozen stars. So it means that if you have, for example, in how this object, black holes can appear due to modern recent astrophysics view. So if you have a star, this star live due to the fact that from one point we have gravitational forces who try to collapse this object. From another side, we have radiation pressure who are working in opposite direction. So in the star in equilibrium in this case, and radiation pressure we have due to the nuclear reaction inside the star. But as soon as all elements was burned and this reaction stopped due to the fact that you already used all, I can say gasoline, yes, in the star. Finally, this will explode, and the outer part will distribute as a supernova, and the inner part, will collapse. So inner part will collapse, and it can be three possibility: white dwarf or neutron star, or if this nuclear of the star is really massive, finally it will be black hole. So, and the idea was that if nothing can't prevent this collapse, so it means that this object will collapse. So it means to be under compression so quickly and compact that finally it will create this black hole. So if the mass more than some limit. And black hole, as I already said, this is hole in space and time, also due to the fact that nothing can go outside of this volume, which is limited by the gravitational radius. So, and the surface also called gravitational horizon. Gravitational horizon. So horizon, understandable, what is it? So we know what is a horizon. It means that when we look on the sea, we don't know what's happened far from than horizon. So as soon as some signals will not come to us. And the same for black hole. But for black hole, it looks like in principle, we can't see what is inside black hole. So if something falling down on black hole, we lose on information. Also the point that black hole, and again, you can immediately to obtain the relation between omega emission and omega observation, so which we showed before for gravitational field. In this case, we just need to put instead of this one, we need to put the observation, omega observation equal square root the 1 minus Rg divided on R omega emission. So it also will work here. So if we have an emission which go out from black holes, it will be also finally more red to go to the red side. What is also important, and there is such a kind of theorem which was formulated by Hawking, that black hole doesn't have hair. So it means that, for example, if you have before something, some special property of the object, for example, it was before star, beautiful. Okay, it says that. So the star had a hair. Hair, it means that. So you have a some face, and you have some hair, and you can. It's by funny. It was called the theorem like this, because you can even from some side recognize the person, or this person like this, or this person like this. Okay, consider that this is believe me, I can draw better than this one, but okay. So the idea is that the property of the person you can describe sometimes some hairdressing. So and this we can connect with astrophysical object or with some physical object. So if you have a star, and this star you can identify with many parameters. This is temperature, this is density, this is mass, this is spectrum, so and so on. This is color, and many parameters. This is composition of the elements, like this. So this object has some individuality. But as soon as this object died, so it means that it's under this stretching, the black hole, collapsing black hole, and we have a black hole. So this object lost all individuality, because black hole, and we can see from this solution, can be identified only with the mass. All these things, beautiful things, which was before, disappeared. So why? Because in this solution, Schwarzschild solution, so you can see that we have only one parameter, and this is gravitational radius. And this gravitational radius depends only on mass. So in this theorem called, it means the theorem formulated like this: the black hole doesn't have a hair. So it means that no individuality. Okay, time is gone. So of course, about black holes we can speak a lot. Just 1 minute, I would like to finalize it. Sometimes I met a question. If by chance you will need to jump in black hole, no, me, for example, consider such a kind of gedabking experiment, in which kind of black hole is much more safely to jump, more massive or less massive. So by the way, you can calculate that since gravitational radius equal to Gm divided on c square. From this you can calculate, and this is extreme radius, which the object with mass m can reach the sizes. So, for example, you can calculate that if mass equal 1 solar mass, so if you want to take our sun and create black hole, you need to stretch it, to collapse it to the size equal approximately 3 kilometers. So it's really you need to make this object incredibly dense. So, and as soon as you collapse this mass in the volume with this radius, so it will become black hole. The biggest black hole, and for example, this black hole, if we speak about stars, it's called stellar black holes. There is also a supermassive black hole, which are in the center of galaxies, and maybe the hugest black hole. This is 10 in 10 solar masses. I'm not sure exactly because I was working with 10 at 9 solar masses. So it's in principle, this is in quasars. In AGNs, active galactic nuclear in quasars. This is much more huge object in the universe. I mean, in sense of huge, in sense of unique object. Of course, we will have constellation clusters like this. So, but this is unique object, and this is one object which can be so massive. And you can see that, for example, for this supermassive black hole, the size of black hole RG, it will be, so if this is like this, we can really to calculate that this is 10, 9, okay, multiplying on 3 kilometers. So this is really not incredibly big, but in any case, it's not big hole in space and time. So, and just to finalize this discussion about black holes, as I said to you before, so if you would like to understand what it means that if, for example, some body go down to black hole, the one of the problems that this body will feel the forces. I forget this word in English. Just a second, I will check. Tidal, so just go out for me. The tidal forces, since the gravity, the space is so curved in the vicinity of black hole, so it means that each point of the space, it will be a very huge gradient of forces. If we will use this, the storm of the forces, which is not good for general relativity. So, and it means that if you have a body, each point of this body will, feel some tidal forces, and finally this body can be, so stretch the space like this. Which object, mathematical object, or say the object from Einstein equation, is responsible to determine these tidal forces? This is exactly Riemann tensor. So, and if you will calculate the components of the Riemann tensor, for example, one of the component tau, I remember. So it will have a proportional sign, doesn't it? RG divided on R cube. And others too, in principle, many of them, they are proportional such a kind of ratio. And what tell us this ratio? It means, so proportional m divided on R cube, okay? So it means that if a black hole is small, It's better. Okay. I write, of course, correct, maybe. So this is like this. And if we will look the tidal forces on the surface, it means that we need to consider R next to RG. And in this case, I will put like this, okay? It will be proportional 1 divide RG, so I put points because many components of Riemann tensor will be like this. 1 divide on gravitational constant, so 1 divide on m. It means that if black hole has a bigger mass, the tidal forces will be less. So if we will consider two cases, big black hole and small black hole, it's much more safely to jump in the big black hole than in the small black hole, because tidal forces here in small black hole here will be much larger than for this huge black hole. It's even understandable because, you know, if you consider the something big, even big sphere, the curvature here, you know, should be maybe less due to the fact that you have a big radius of surface curvature. So, and this is, it will be less. So you just to say about this. Okay, now I can see that we already over. So if you have some question, please ask me. I just for the on the next lecture we will start to work with cosmology. So, and our idea in the beginning, we very quickly consider the gravitational lensing effect, just also what we have from general relativity. And we immediately will start to work with cosmology. So we will find the metric of the universe, as I already said. After this, we solve Einstein equation, and we will obtain cosmological equation, which will tell us about the story of the universe. Do you have some questions? Wow, we need to make Are you here? Now wait, I need to make a screenshot. Okay. Okay, so if you don't have any questions, so I will wait your suggestion about day of the lecture. So principle any day is okay for me. Only not even Monday in the evening, it's also okay. And the after lunch. So okay, if you don't have any questions, see you next week.
Thanks.